All right, in Unit 6, Lesson 3, we're going to start to explore logarithms. And so we don't know what those are yet, which makes this one of my most favorite units because I don't have to build on someone else's foundation. Instead, we get to kind of lay this groundwork of what logarithms are. Obviously, there will be some challenges there of learning the new notation, learning the new language. It's kind of like when you're first introduced to sine, cosine, and tangent, and then there's this new operator, this button that you press in the calculator, but it has meaning, and it is in operation, and it is related to things that we've already done and explored. But I love to engage with this. It makes it one of my most fun couple lessons. This one and then lesson 4 will be probably 2 of my favorites. And hopefully this makes for a great end to our school year, and let's kind of see how this goes together. Our job is to write these exponential relations in logarithmic form, and then of course vice versa. We're going to go from logarithmic form to exponential form and be able to navigate between those things. If we're able to do that, then we will be able to not only evaluate logs, but we'll be able to solve logarithmic equations and exponential equations. And so this gives us kind of a mechanism for exploring and understanding that. You will need to have a calculator today. It's just a basic scientific calculator can do the trick. Graphers are great, but again, not necessary. So here, we're going to get to solve these things. I don't know why I have solve written twice on there, but whatever. If we're solving this equation, we're going to perform the inverse of subtraction is to add. The inverse of square root is to square. All right? The inverse of multiply by 2 is to divide by 2. But the inverse of exponentiation is kind of like tough. Like if you don't know that 8 is 2 cubed, then you would not know that x would be 3. So we've got to have some kind of mechanism for us to handle these, this inverting, this undoing of exponentiation. So sometimes we can solve those because we know things, but that requires us to know that 8 is 2 cubed, all right? Which you should know. Hopefully you do. But again, we are learning about how we apply these inverse operations all through algebra and pre-algebra, and now we're going to think about inverting logarithms. And so here is sort of a working definition of the logarithmic relationship. So the inverse of an exponential function y equals b to the power x is log base b of y is equal to x. So essentially what we're doing is we're taking this base and it becomes the base of our logarithm, log base b of y is equal to the exponent. X stays by itself. So this gets the x out of the exponent. Another way for us to understand that is we are taking the log base b of both sides, log base b of b to the x. And so when we do that, this gives us log base b of y, but it gives us just the exponent. Log base b of b to the x is just the exponent. And we'll talk about the mechanics behind that in lesson 4. So this is that relationship. This is how we get from an exponential form to a logarithmic form. But likewise, we could take a log, base b of y equals x, and we could make this the base on the other side of the equal sign. So these are inversely related operations, inversely related functions. There are some special logs. The log button that you see in your calculator is actually log base 10. The log, whoops, the log base e, I didn't type that correctly, is the natural log. And so let me write that, natural log. Whoops. So log base 10 of y, we write as just log y. Log base e of y, we're going to write as ln of y. This stands for the natural log. It seems like it's written backwards, but that's because every other language describes their logs in reverse. We say natural log, they say log natural, and so it's English's fault, not math's fault. So here we go. We've got common log and we've got natural log. This will kind of help us navigate how and when and why to use these buttons in our calculators, right? This is the log button in the calculator. This is the natural log button in the calculator. But what do we do if we have a different log? And so we're going to explore that as we work through this unit, specifically next time, but then again on in lessons 5 and 6. So here, we have some exponential expressions, equations, relationships, and what we want to do is write them in logarithmic form. So again, this is the base, which means I would write this as log base 2, because that's the base of my power, of this value is equal to the exponent. All right? The base of this is 1/2. So we would say that the exponent is equal to the log of the base 1/2 of 1/8. Over here, the exponent is equal to log base 10 of 0.0001. Another way that we could write that is just the log of 0.0001. All right, log base 10 is the same as just the log button. All right, and so now we want to understand how can we evaluate these, how can we think through these. These relationships do indeed hold. And so the question is, how would we be able to evaluate this if I didn't know that this value was equal to 5? All right, and so we're going to be exploring that here today. What about taking it from log form and rewriting it in exponential form? So again, the way that we do that is we take the base and put it onto the other side. And the number that this equaled is now the exponent. So this is now equal to the base to the power. Here, you cannot see what the base is, but we know common log means the base is 10. So it means 9 is equal to 10 to the power 2x. Here, the natural log has a log base e. So this number is equal to e, that natural number that we've been learning about, to the power x minus 2. So this gives us this relationship. It gives us this mechanism for navigating from exponential form to log form. We're going to practice this a bunch so that we don't mix up what numbers go where in this relationship. All right? We want to do that well. So we're going to practice it a ton. A lot of it's going to seem repetitive and redundant. But if we don't do a good job with this, then we can't do the things that we need to do as we move forward. All right, so for example, one of the things that we need to be able to do is evaluate logarithms. And so we don't really have in our scientific calculators a method for evaluating this. It's going to require that we understand this relationship. So the way that we would evaluate these is we would say, well, this equals something. And in algebra class, whenever we don't know what it is, we call that something x. And so 81 is equal to 3 to some power, which is helpful for us because we might know, we should know, we could know that that means that x is equal to 4, right? 3 to the 4th power is 81. And if 3 to the 4th is equal to 3 to the x, then that means that 4 is equal to x. Again, if you're having trouble exploring that, then you can have in your calculator y equals 3 to the x, and what value of x is going to make this output equal 81. That's a way that we can explore that. All right, 1/32 is equal to 64 to the power x. That's how we're going to understand that relationship. You might not see how these are related, but we do know that we need an exponential relationship. Well, this is the same as 1/2 to the 5th. This is the same as 2 to the 6th, now to the power x. That requires us to know our powers of 2. Do we know those powers of 2? Maybe, fingers crossed, hopefully. We should know some of those. We've been dealing with a lot of these in our radicals unit, and when we started our semester with our cubes and our powers of 4 and all that awesome stuff. So this right here, this 2 to the negative 5th, this 1/2 to the 5th, is the same as 2 to the negative 5th power, right? We know those rules from Algebra 1, those rules of exponentiation. And if we have a power to a power, that means we multiply those exponents. So this means that 2 to the negative 5th is equal to 2 to the 6x. So these powers, since these bases are equal, these powers have to equal each other, which means that -5/6 is equal to x. All right? We took something that was a little crazy here, very much an Algebra 2 equation. We made it an Algebra 1 equation, and we solved it by dividing. Right? This is 6 times x, we just divided by 6. So that requires us to know some things about numbers, some numeracy skills, and that might be really challenging for us. And I'm ready to deal with that challenge and take that head on. I hope that you are as well. Let's look at a couple of these. All right, and let's try to have you explore this one. I'll have you do this one. You do All right, but over here I want to address this, because this is a situation that is undefined. There's no solution to this equation, so I can't define what this thing means. Let's explore. Negative 8 is going to equal 2 to some power, right? If I'm going to take this base and make it the base of that, for that exponent, I say negative 8 is equal to 2 to some power. Well, I know that negative 8 is the opposite of 2 cubed, all right? But this will never equal a negative number. I can't make 2 to any power end up being negative. Let's think about that. What if we had a negative power? Well, that's just going to be 1/8. 2 to the negative third is 1 over 2 cubed. And that's not a negative number. So that's still positive. I can't change this. So that means that this log base 2 of negative 8 is undefined. It doesn't exist. There is no log base 2 of negative 8. All right? Over here, though, I would like for you to try letter D. I know you're not a fan of those always, but we're going to give it a shot anyway. All right. Now, this application part, we might run into some bumps here as we try to understand how to apply logarithms outside of algebra class. The first part of this, we want to make sure that we can do that. All right? So hopefully the first part of our lesson, we're good. This is application, and this is kind of to wrap this in cross-curricular wise with chemistry or earth sciences. And so you've already been exploring this in your chemistry classes from what I understand. I don't know if you've dealt with the magnitude of an earthquake with relation to its seismic energy measured in joules and blah, 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 blah. But this is this explains those relationships. We explore acidity in chemistry class as a concentration of hydrogen ions. That's how this works. I'm a big fan of chemistry. It's really hard for me, but I love chemistry because it's a great application of some higher level math, right? Chemistry is tough because math is tough. All right, so here is an example. The pH of an apple is about 3.3 and the pH of a banana is 5.2. Find the concentration of hydrogen ions in each fruit and which one is more acidic. So we have some things to talk about, like how do you know if something's more or less acidic, and so we'll discuss. The pH of an apple is 3.3, is going to equal the negative log of this H+. So the way that we understand this is if I change this, multiply both sides by -1, I get this. And we know that this log is base 10. So 10 to the negative 3.3 is equal to that concentration of hydrogen ions. Whereas, with the same formula, I take, 5.2 is equal to the negative log of this concentration of hydrogen ions. So that means that negative 5.2 is equal to log base 10 of that concentration. And so 10 to the negative 5.2 is equal to that concentration of hydrogen ions. All right, so here's what we notice. I don't have to type these in, all right? I can if we'd like to, but it should give us a little bit of a clue. 10 to the negative 3.3 gives us 0.00, oops, there's one more zero, 5012. All right, that's what we have for an apple. And then over here, 10 to the negative 5.2, this gives us 0.12345,631. All right, this is for the banana. But that's a separate question from which one is more acidic. There's the concentration of hydrogen ions for an apple. Here's the concentration of hydrogen ions for a banana. But this scale, the pH scale, determines acidity. All right, a pH of 7 or higher is basic. All right, or I guess greater than 7, pH greater than 7. But if pH is less than 7, it is more acidic. So since 3.3 is less than 5.2, the apple is more acidic. All right? All right. In fact, here you go. 7 is neutral. That's why this is on a separate slide. But what we can do is we can do this work to figure out if this is the amount of hydrogen ions, or I'm sorry, the concentration of hydrogen ions, then that will let us know what the pH is. So the pH for lobster is the negative log of 3.71 times 10 to the negative 8th. And so we can legit just type that in the calculator. There's a log button, 3.71 times 10 to the negative 8th, and it will evaluate that. Oops, I forgot the negative. And it gives us 7.43 for lobster. Okay? So the pH is about 7.4306 for lobster. All right? You find it for shrimp. And then tell me which one is higher. If it's higher, then that means that it is more basic. Which one is lower, that means it's going to be more acidic. All right, but you can kind of say, hey, this is about 7.43, so it's pretty neutral. It's a little more on the basic side of neutral. All right, for lobster, I don't know if you've ever eaten lobster or shrimp, but it should kind of give you an idea of what that tastes like and how that affects, or how that is dictated by the pH level. All right, going into seismology. All right, if we're talking earthquakes, and we're talking about magnitude, and we're talking about how strong these things are, one of the things I want for you to understand is an earthquake with a magnitude of 4 is 10 times weaker than one with a magnitude of 5, right? So that's kind of how those are measured. So in this situation, the largest earthquake in Kansas released blah, 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 blah joules of seismic energy. What is the magnitude of the earthquake? So X is 4.47 times 10 to the 19th, and that's going to equal 10 to the 1.5 m plus 12. We're solving for m, which means that we're going to rewrite this in logarithmic form. I'm going to say log base 10, which I don't have to write the 10, of 4.47 times 10 to the 19th is equal to the exponent here, 1.5 m plus 12. So if I want to solve this equation, let's leave all of this written the way that it is. But we're going to subtract 12. Log, I'm not going to use the 10 there, of 4.47 times 10 to the 19th minus 12 is equal to 1.5 m. But then on both sides, I'm going to divide by 1.5. We have to be very attentive to using our parentheses if we're using our calculators to say that when I divide by 1.5, I will get m by itself. And so we can approximate that. Sorry for the handwriting there. I'm going to approximate that. Parentheses on the outside, the log of 4.47 times 10 to the 19th, close parentheses, minus 12, close parentheses again, divide by 1.5. Then to give you a magnitude of about 5.1. So that is our magnitude. That's a 5.1. Usually they say on the Richter scale or whatever. Maybe there's a different scale now. All right, but that would give us a clue of how close or how powerful that is compared to, let's say, this one. All right, so for here, this one, you find and compare. All right, compare the biggest one ever in Kansas. And let's see that relationship. What we want to be able to do is use logarithms to understand exponential relationships, but likewise use exponential relationships to explain logarithms.